Thank you very much, Evie. That was and Carrie, if you're ready to go, this climate predictions and what the future looks like for ground-hornbills again segues beautifully into Carrie's presentation now, the effects of high temperatures on nestling growth and physiology in the southern ground-hornbill. Over to you, Carrie.
Hi everyone, sorry, I'm just getting set up here. Let me just see what this looks like.
No, it's the wrong way. We're getting there.
Sorry.
No panics.
This one.
Perfect, Carrie.
You see the presentation view?
Yep, that's perfect.
Yeah, okay, cool. Yes, so hi everyone, my name's Carrie and I'm a student at the Fitzpatrick Institute. Recently enrolled last year, but I've been lucky enough to be working on the APNR Ground-hornbill Project for a few years now. So I'm going to tell you a little bit about what I'm looking into, the effect of high temperatures on nestling growth and physiology in these southern ground-hornbills. So for those of you who don't know much about the project, the APNR Ground-hornbill Project has been running for 20 years now. And when the project first started, it was noticed that there was a lack of nesting sites within the area. So these artificial nests were installed, and amazingly, these birds took to them so quickly, and they were incredibly happy to breed in these artificial nests. So since then, the project has been installing nests strategically throughout the area. And obviously with us knowing where the birds are nesting, it provided the perfect opportunity to monitor the nests, the breeding of the birds, and to conduct all sorts of research and try to understand the species better in a wild population. So this site is called the APNR, the Associated Private Nature Reserves, located in the northeastern part of South Africa. And this area is comprised of 5 privately owned reserves, an area of around about 200,000 hectares. And within this area, we have about 26 known groups. I'm sure there are a few little groups that we don't know about that are popping up now. But you can see these territories kind of mapped on the pentads on the left here. And within each territory, we try to provide a nest for the birds. So we have about 29 known nesting sites, soon to be 30. We're going to pop a new one up here where there's a space for one in Balule. But within all of this area, there's only 3 natural nests that we know of. So it really shows the importance of these artificial nests for the birds. And in this area, the temperatures reach well above 30 degrees in the summer, often high 20s in the winter. And the annual rainfall is around 500 to 600 millimeters. Summers are very hot and often humid. Winters are incredibly dry and warm. So with the climate in this part of South Africa already very warm, and over the coming decades, we know that South Africa is likely to experience more prolonged periods of high temperatures and drought. This will result in population shifts, biodiversity loss, and for ground-hornbills, this could mean dwindling food availability and temperatures above their own thermal limits. So my research aims to look at some of these more direct effects of temperatures, especially on the ground-hornbill nestlings. And studies on many other bird species, which are usually done in more desert environments, such as the Kalahari, have found that high temperatures lead to a decrease in growth rates. And this can be because the chicks are investing more energy into actually regulating their own body temperature rather than into the importance of growth. And it can also be that they're receiving less food from the adults as they deal with their own thermal needs. So the adults could be spending less time foraging, seeking shade, and there could also just be less food available during these times. And this often has carryover effects on the chick, reducing their fitness and survival rates in adulthood. And these are some results from Kyle's research, which he's going to talk to you in more detail later, where he shows that chicks fledge lighter when they experience higher temperatures. So I want to look a little bit more in depth at this. So to look at nestling growth and condition, we measure the chicks at 6 different stages. We try to keep this to minimal amounts of visits to the nest. We install eye buttons into the nest to record the temperatures inside, and we find out the provisioning or feeding rates from our camera trapped footage. If we piece this all together, we can look at whether the negative effects of growth arise from food provisions or from the direct effects of temperature. And if we find that nest temperature plays a bigger role in this pathway, then this is something we can help them with, and we're actually currently doing. We're working with Mabula to provide better nests, and we make sure that we put them in shadier canopies and things like that. So unfortunately, I don't have results of this pathway yet. We need a couple more seasons of data. As we know, the birds don't produce many chicks a year. So I think in 1 or 2 more seasons, we should have enough data. What I do have is a growth curve of 13 nestlings. And this is really interesting. You can see that individuals, they vary widely with their mass, sometimes even being a kilogram in difference between the birds. And you can see that the mass kind of tapers from about 60 days. Another thing I hope to look at is this telomere length and telomere shortening. Now, telomeres are the non-coding sequences of DNA that protect chromosomes during replication. And physiological stress from high temperatures, as well as less food, can lead to DNA damage, resulting in the shortening of telomeres. And telomeres usually shorten with age, but it's also associated with environmental stressors. And a lot of telomere shortening takes place during rapid growth when energy expenditure is high. And there's this link between early life telomere length and individual lifespan or condition. So if we look at this, this should provide an indication of the quality of environmental conditions experienced in early life and their expected survival. And this is really interesting for the ground hornbills as such long-lived species. So to look at this, we take blood from the chicks when they're very young, and then again just before they fledge, to see if there's any shortening of these telomeres. And hopefully next year I'll have some results to show you from this. So another important thing to look at is what's going on away from the nest. How are the rest of the group dealing with these high temperatures? So ground hornbills, we all know they spend most of their day walking on the ground, foraging for food. So they're exposed to a lot of direct sun as well as ground surface radiation. So we specifically want to ask the questions and find out whether they're experiencing foraging and thermoregulation trade-offs, whether there's a thermal cost to provisioning, and what are their actual thermal limits. So we know this study by Andrew Rees and Lucy and Andrew McKechnie came out last year. A really interesting study on how the ground hornbill beaks act as thermal regulators. And this is a non-evaporative cooling method where heat can be lost by adjusting blood flow to these areas. and they can dissipate up to 75% of basal metabolic rate this way. And this is something the birds do without having to think about. So in the thermal imaging pictures, as temperatures increase, you can see the beak and facial skin changing colour from purple at the top when it's quite cool, and it turning to orange and yellow when the temperature heats up. And the graph just shows the surface temperature of the beak increasing as the air temperature increases. So there are a few other ways in which the birds can adjust their behaviour in which to cool down by retreating to a cooler, shady microsite, usually up into a tree. But this can result in missed foraging opportunities for the birds. The birds can wing droop and use tyloerection to allow increased airflow to the skin. They pant to allow for evaporative cooling. And then we also see this deflated facial skin when there's a decrease of blood flow to the area. And we notice this on hot and cold days. So they must be minimizing both heat gain and heat loss by doing this. And something else picked up by Andres and his thermal imaging was this nasal watering, sometimes seen at very high temperatures. So to do this study, we look at the camera traps. So I record what the birds are doing when they arrive at the nest in terms of this heat dissipation behaviour. So you can see this male is wing drooping. He's now started to pant. Now he's fed the chick in the nest. He's even showing some nasal watering there and some tyloerection. So that's how I record all these behaviours. And again, another example. So these birds they're facing substantial trade-offs on these hot days, and they've chosen to feed the nestling rather than eat the food themselves. And this is very costly to them because they're out in the heat, expending energy, losing water to evaporative cooling, without actually gaining the food reward for themselves. So I do have some results of this, and I hope I explain it okay. So in this graph, the zeros along the bottom are when a behaviour is not witnessed, and the ones along the top are when it is witnessed on the camera traps. And this is for the behaviour of wing drooping. And this line, the line is the interaction between the two, so the inflection point, sorry. And wing 50 is the temperature at which individuals are likely to be doing the behaviour 50% of the time. So it's this crossover between not doing the behaviour to doing the behaviour. So above a temperature of 35 degrees, a male is more likely than not to be witnessed wing drooping. And with tyloerection here again, this seems to be happening at hotter temperatures, but it's quite misleading because it's hard to separate this tyloerection from heat dissipation behaviour and social interactions, because especially the youngsters seem to do a lot of this tyloerection during social engagements. So that's something we will hopefully get some more data on. And what's interesting is the birds seem to pant before wing drooping and tyloerection, which is usually what birds resort to last. So this is super interesting. So we do this, we take this behaviour once the birds have fed the chick inside, because obviously when they've got food in the beak, they can't pant. So we look at this behaviour after the food has been provisioned. And you can see here a temperature of 31 degrees for pant 50. So above this temperature, a male is more likely to pant than not. So these are quite low temperatures. And panting is very costly in terms of water loss. So this might be because these birds are large, they have larger water stores, and a very water-rich diet. And the reason why we separated the males, females, and immature birds is that they all contribute differently to the nest provisioning. So they all have different roles, which is something Kyle will explain further in his results. And we have this throat deflation, which we see a lot in the females as she comes and goes in the nest, not as much in the other birds. So again, at low temperatures, we see this, and at high temperatures. So they must be minimizing and maximizing heat loss and gain by doing this. The nasal watering, nasal 50 occurs females before males, from a temperature of 40 degrees onwards. So these are temperatures that we do experience in the low veld quite regularly and are likely to experience more regularly. Another thing I'd like to look at with this is whether these heat dissipation behaviours are mediated by the dominant status of the individual. And to record this, I'll look at any dominance interactions such as chasing, avoidance behaviours, attacking. But it's not been as easy as I thought it would be, as these birds are usually quite polite at the nest. There's occasional kind of interactions like this, but generally they're quite polite and they'll wait their turn. And the theory is that dominant birds might have more access to resources such as food and shade, so they can afford to pant at lower temperatures than subordinates. And it's important that we don't just look at these camera trap images. We really want to get a picture of the whole scene of what's happening away from the nest as well. So from photographs and videos that people send in to us, we can record heat dissipation behaviour. And it's important that we also get non-heat dissipation behaviour too. And then we can pull in temperature and humidity data from a nearby weather station. And this should help us to build more accurate results with more data points. So for the camera traps, we were sitting at around 3,000 observations. For our sightings in the field, we're at about 300. So we really need to get these into the thousands for it to be an accurate representation. So I urge you to, if you do have photographs and videos and you know where roughly it was taken and you've got the date, time and location, please send that in to us. But also please keep your sightings going to Mabula as well. And we do share our sightings with each other, but it would be we particularly need photographs and videos. And this is some examples of what we've been receiving, some really great images, which really helps us with this study. And this was quite a striking image. A female collapsed on the ground, obviously very at risk of not only hypothermia as she struggles to maintain her body temperature, but she's also very vulnerable to predation in this state as well. So we hope that this research will help us to begin to understand the thermal tolerance of these birds. An additional research question, which I hope to answer, is finding out whether females modulate egg size according to environmental conditions and social factors, and also whether egg size is correlated with nesting growth and telomere length. So to sum up, this should hopefully give us the first insight into the physiological stresses on wild ground hornbill nestlings, and to find out whether provisioning is more important or if temperature is more important for growth. And the heat dissipation behaviour could help in predicting the species' vulnerability to climate warming, which should give improved guidance on the conservation needs. So we want to see more of these nestlings fledging, healthy and happy. So that's it. Thank you very much for listening, and a huge thanks to all the supporters and people we collaborate with, and for all the reserves who allow us to conduct this research. I'm happy to take any questions.
Thanks, Carrie. That was awesome. There's a question from Yvette. Do your camera traps measure temperature to correspond with eye button data? Is that something that you've compared?
No, we can't rely on the camera trap temperatures at all. They're wildly wrong. So we just use the nearest weather station data, which is it's not great, but it's what most studies do anyway. So it's more reliable air temperature data. And we do have a weather station within the reserves.
Cool, thanks. And then there's a question from Jared. Are the males reflecting more heat stress actions because they're more active or because there are more of them?
I think it's more that they're more active. Yeah, we've definitely got more observations of males, obviously, because there's more males. But these results definitely show that males are heat dissipating earlier than females, which suggests that they are doing more work. And also Kyle's results, which you'll see soon, also show this.
Cool, thanks. I don't see any hands up. Are there any other questions for Carrie? So Carrie, we'll keep pulling out any of the heat stress images as Kyle goes through, as Jared goes through each and every photo ever published. Yeah, and hopefully we can be able to support you with that and see if we can get you more images.